Good morning, Chemistry 122 students. This is our lesson on thermodynamics, which is chapter 12 in your textbook. And today we're going to look at the different laws of thermodynamics and the concept of entropy. Here we see Miss Annie celebrating at one of my birthday parties, and the candles are a good illustration of the energy that is emitted by an exothermic reaction, the combustion of paraffin. Okay, so the first thing we kind of want to do is get a big picture image understanding of reactions and the feasibility of reactions. Okay, so let's consider, we've looked at this reaction before. Nitrogen undergoing reaction with hydrogen to produce ammonia. Okay, so if I'm a chemical industry and I'm trying to produce this product and I'm trying to make a profit off of the production of that product, obviously any energy affiliated costs with making that reaction go is going to go into my cost. And so if I want to minimize my cost of producing that product so that I can sell it to consumers at a very competitive price, I want to get a handle on the cost of production. So what kinds of aspects of this reaction are going to be important in terms of the costs and from an energy perspective? Okay, the first thing that I might want to be concerned about is the speed of the reaction. And we learned all about that in a previous chapter on kinetics. How fast is the reaction? Okay, the things that dictate how fast the reaction is has to do with the mechanism. If our reactants start out at this energy and our products end up at this energy, okay, the thing that dictates how fast that reaction goes is the energy barrier, the path that that reaction goes through. And so the activation energy is the magnitude of that energy right there. Okay, and that dictates how fast that reaction goes. Okay, that aspect of the reaction is going to affect feasibility, and you want to do everything to optimize the speed of the reaction, maybe add a catalyst, etc. But that has nothing to do with the thermodynamics of the reaction. Thermodynamics has to do with something known as spontaneity. Does the reaction go spontaneously? Meaning, when I mix my two reactants, does it just go, or do I have to do work to make it go? And so that is the other critical aspect of a chemical reaction. And these two things are completely independent of one another. So the kinds of things that are going to influence whether the reaction goes spontaneously or not, there's two things. One is the enthalpy change. We've learned all about that in previous chapters. That's the delta H. If it's exothermic, okay, it's going to tend to be spontaneous. Okay, but enthalpy alone does not dictate whether it's spontaneous. There is another dependence, another parameter. It's called entropy, which is a measure of the disorder in the system. And when the entropy change is positive, that tends to be spontaneous. Okay, all right, so thermodynamics has to do with, does the reaction go spontaneously? It depends on enthalpy and entropy. Kinetics depends on the speed of the reaction. It has to do with the magnitude of the activation energy as dictated by the mechanism. And these two things are independent of each other. You can have a spontaneous process that takes a really long time to go, or you can have a really fast reaction that's non-spontaneous. Okay, so let's review the different laws of thermodynamics. Very quickly, the zeroth law tells us the concept of the relationship of heat and temperature. So if you have two bodies that are touching each other, and the first body has temperature 1, the second body has temperature 2, if temperature 1 is greater than temperature 2, heat will spontaneously flow from body 1 over to body 2. Okay, so that kind of encapsulates the concepts within the zeroth law of thermodynamics. It establishes the notion of temperature and heat. First law of thermodynamics is the conservation of energy. Okay, remember the energy of the universe is a constant amount. We can't create or destroy energy. Okay, so in effect, if you think of the universe as being comprised of two different things, a system and surroundings, that total energy has to be the sum of the energy within the system and the surroundings. An outcrop of the first law of thermodynamics is the concept of internal energy. And internal energy, okay, of a chemical system, okay, is predominantly the sum of energy in the form of heat plus energy in the form of work. Okay, so Q is heat, W is work. All right, and so for chemical systems, any potential work that might be done is pressure volume work. Okay, and there really will only be pressure volume work done if we have a gas and we are not at constant pressure. But if we are at constant pressure, okay, this work term is 0. So in this equation, that work term drops out. And so the change in internal energy for any chemical process is simply at constant pressure is simply going to be the heat gained or lost. And so this introduces the concept of enthalpy, which is the heat gained or lost in a constant pressure process. And remember, delta H is enthalpy. It's a state function, so a change in enthalpy is the final enthalpy minus the initial. It does not depend on how we get there. Okay, and so from a chemical perspective, remember, we think of this as the enthalpy of the products minus the enthalpy of the reactants. Okay, and there's a number of ways we can predict the enthalpy change for a process. And the second law of thermodynamics introduces the concept of entropy. The second law tells us that the entropy of the universe is constantly increasing. Okay, so I guess we kind of need to know what entropy is. Entropy, typically denoted by a capital S, is a measure of the disorder in a system. Okay, big word, disorder. So chaos, randomness. Buildings over time, unless we maintain them, are going to crumble. They go from a state of high order to disorder. That is the concept of entropy. It's a measure of that. And so for a process, like a chemical reaction or a phase change, the change in entropy is going to be positive if we go from a state of greater order to greater disorder. The entropy change is going to be negative if we go from a state of disorder relative to a state of greater order. All right, so we'll go through specific examples of chemical processes that are going to have either a positive or a negative change in entropy. Okay, but that's the important thing to remember about it. Entropy is also a state function. And as previously stated, state functions only depend on the final and initial state. Therefore, a change in entropy is going to equal the total entropy of the final minus that of the initial. And if we're talking about chemical reactions and processes, this is our products minus reactants. Okay, and finally, the third law of thermodynamics defines essentially what is an understanding of absolute zero, which, as you know, is 0 degrees Kelvin. Okay, and basically what the third law tells us is that the entropy of a perfect, pure crystalline substance at absolute zero is 0. Okay, so if we had a sample of sodium chloride in which the sodium ions and the chloride ions were perfectly ordered, okay, perfectly ordered, there were no impurities in it, no single ion was out of place in the slightest way in the crystal structure, and if we were at absolute zero, the entropy of that pure crystal would be 0. So there are no negative degrees on the Kelvin scale. That is the lowest temperature we can obtain, and it's actually defined in terms of entropy. Pretty cool. Now that we know what entropy is, we want to start thinking about actual chemical reactions and processes, phase changes, and group them into the types of processes that are going to yield an increase in entropy. So entropy is disorder, so we're thinking about those kinds of processes in which we go from a state of greater order to greater disorder. All right, so first type of reaction that this is going to be true for, anytime we have a big molecule or bigger molecule that breaks up into 2 or more smaller molecules, we're going from a state of higher order to disorder. Entropy change is going to be positive. All right, a really good example of this, fun reaction. 2 moles of a compound with formula C3H5 NO3 3. This substance a liquid at room temperature. Anytime you see a bunch of nitrate groups, think explosive. This is nitroglycerin. Alrighty. That big molecule breaks up into 3 moles of nitrogen gas, half a mole of molecular oxygen, also a gas, 6 moles of carbon dioxide gas, and 5 moles of water vapor. All right, this is typical of an explosive. You have a big molecule that breaks up into a bunch of gaseous phase molecules that create pressure. That's where the explosion comes from. Okay, oftentimes generates heat. The enthalpy changes are usually exothermic. Alrighty, so from just a chemical analysis standpoint, you have 2 moles of reactant in the balanced equation, yielding, oh, let's see, let's count, 3.5, 9.5, 14.5 moles of product. So a big molecule breaking up into many smaller molecules. That is going to have a positive entropy change. We are going from a state of higher order to disorder. Okay, next group of reactions that are going to yield a positive entropy change, very simplistically, since the gaseous phase is so characterized by disorder, anytime we have a reaction in which the moles of gas within the products is greater than the moles of gas in the reactants, we predict an entropy change that is positive. So another example of a reaction for which that would be true. Oh, if we have calcium carbonate, ionic compound, solid at room temperature, eggshells are primarily calcium carbonate. If you put calcium carbonate in a solution of hydrochloric acid, we actually produce calcium chloride soluble salt. We produce carbon dioxide gas. And we produce a molecule of water. Okay, double check if we're balanced. 1 calcium each side, 1 carbon, 3 oxygen, yes, 2 in the carbon dioxide, 1 in the water, 1 hydrogen. Actually, we need 2 HCl. Ah, don't we? Yes, we do. Okay, now the reaction's balanced. Okay, so please notice in inspecting this reaction, how many moles of gaseous reactant we have. Are any of our reactants gases? No. So we go from 0 moles of gas in the reactants. And as we inspect the products, oh, look, I have a mole of CO2 gas over here. So 1 mole of gaseous product. Okay, so that's an increase in the moles of gas. Therefore, I predict the entropy change of this reaction to be positive. Okay, finally, phase changes. Okay, we need to intuitively think back about what we know about the different phases of matter. The solid state, atoms, molecules, and ions are fixed in place. They do not move. It's highly ordered. If we go from the solid state to the liquid state, okay, let's begin with that one. Solid state to the liquid state. The name, remember, melting or fusion. So highly ordered. Okay, as we go to the liquid state, we break intramolecular forces. The atoms, molecules, or ions are freer to move about. So that is certainly going from a state of greater order to disorder. And so melting or fusion is going to have an enthalpy change that is positive, increase in entropy. We also know what happens to enthalpy, heat. Because we're having to break intermolecular forces to make that transition, this is an endothermic process. All right, keep it going. Liquid to the gaseous state. That is vaporization. Okay, once again, we have to break the intermolecular forces between the molecules. They then are free to move about in the gaseous phase. That is going from a state of higher order to disorder. That is a positive change in entropy. Because we have to break those intermolecular forces, it is also endothermic. And then you can do the direct transition from the solid state to the gaseous state, the sum of the previous two. And so that obviously is going to be an increase in entropy and endothermic. Okay, keep in mind if we go into solution, okay, if sodium chloride solid state goes into aqueous solution, in which the water molecules have pulled apart the ions out of their highly structured crystal structure, and now they're floating around. They're physically moving within the solution. That is a state of greater disorder. And so the process of dissolution, going into solution, is also one for which the entropy change is positive. All right, and if we are talking about any of the reverse processes here, if you go from a gas to a liquid, condensation, entropy change is going to be negative. Okay, we're going from a state of disorder to order. If you go from the liquid state to the solid state, that's freezing. Entropy change is going to be negative, lost entropy. Or if you go directly from the gaseous phase to the solid phase, deposition, the entropy change will be negative. Alrighty, and if we did the opposite of the dissolution process, remember that's precipitation formation. If the sodium ion and the chloride ion found each other and came out of solution to form the solid, this is a highly ordered crystal, so we're going from disorder to order. So precipitation would have an entropy change which was negative. Okay, now we wish to predict entropy changes for specific reactions. So chemists over years of research have compiled data tables, thermodynamic data tables, in which we have measured the molar entropy of different substances. So shown here is such a data table. This particular one is organized. We have gases here, liquids here, solids here, and the standard molar entropies of each and every substance. So keep in mind that's the entropy of 1 mole of that substance. If we have a reaction that involves 2 moles of that substance, it's going to be 2 times that quantity. Okay, so entropy change is a state function. As a state function, it only depends on the final state, which is our products, minus the initial state, which is our reactants. So just like we did with enthalpy changes, for entropy changes, we can calculate the overall entropy change by looking up standard molar entropy values for each and every one of our products and multiplying by the number of moles of that product. And then we have to do a summation over our reactants, looking up their standard molar entropies and multiplying by however many moles of each and every one of those substances are involved in the reaction. Okay, so let's predict the standard molar entropy change for this reaction given. Okay, we have ethanol reacting with oxygen to produce carbon dioxide gas and water gas. Okay, this is a combustion reaction. Reaction with oxygen to produce CO2 and water, classified as a combustion. All right, first critical thing we do is make sure it's balanced, because our entropy values are all dependent on how many moles of each substance. So balancing, we start with carbon. Carbon first, so carbon on the left, I have 1, 2 carbon. On the right, currently I only have 1 carbon in the CO2, so I must put a 2 out in front. Next, hydrogen. I have a total of 3, 2, and 1, so that's 6 hydrogen left. I need 6 right. Therefore, I need a 3 out in front of the water molecule. Let's get rid of these for a minute. Okay, and finally oxygen. I have 1 oxygen here, and I have 2 oxygen here, for a total of 3 currently on the left. On the right, notice oxygen, I have 4 from the CO2, and I have 3 for a total of 7 on the right. So what I'm going to do is I'm going to come back over here, and I'm going to say, okay, I have 1 in the ethanol molecule, so now I need 6. So I better put a 3 here. Okay, now I'm balanced, and I can follow through with predicting this entropy change. Okay, so I start with my products. 2 moles of CO2 gas. CO2 gas, look under the gases, there it is, 213.8. Next product is water, and it's gaseous. 188.8, 3 moles of it. Okay, now I subtract off the summation over my reactants. 1 mole of ethanol, 160.7. And 3 moles of O2 gas, so look under gases. Okay, doing the math leads us to a entropy change for this reaction under standard conditions of a positive 217.7. Notice moles cancel in all of this, so we are left with units of joules per degree Kelvin. All right, let's do a logic check. We have an increase in entropy. Does that make sense? All right, let's analyze gases. Okay, amongst the reactants, this is a liquid, but we had 3 moles of gaseous reactants. And for products, we have 2 moles of CO2 that's a gas, 3 moles of water that's a gas. So we formed 5 moles of gaseous product. That should net us a positive entropy change, and it does. Okay, so you can see how useful these data tables with standard molar entropies for different substances can be in predicting our entropy changes. So this ends today's lecture, and we will move on with the next topic, spontaneity. Have a great day. And finally, an analysis of the reaction we just predicted the entropy change for. We calculated the entropy change to be a negative 97,933 units, or joules per degree Kelvin. We could convert that to kilojoules per mole by moving the decimal 3 places. So that would be a negative 97.9 kilojoules per mole. All right. Now, is this the sign of the entropy change we would predict? So notice we have a negative entropy sign. That means that we went from a state of greater disorder to greater order. All right, do we expect a decrease in entropy? All right, so if we go back to our rules, let's consider gaseous reactants and products. Okay, amongst our reactants, notice we have, this is a liquid, we had 3 moles of gaseous reactant, and we produced a total of 5 moles of gaseous product.